Yep,
Okay,
started. Okay.
start. Okay, ممتاز. I like to welcome all the attendees for the fourth webinar of 2024. This year will be the focus on production logging tools from different tool manufacturers and software providers. This webinar will be presented by Mr. Hussein Al-Shabebi. He's a petroleum engineering advisor for Baker Hughes company. He will introduce himself at later stage of this webinar. I'd like to welcome his to our webinar series as well and thank him for his efforts. I will make a small presentation. Okay. Yes. Is my screen appear?
Yes.
Okay.
Yes.
Okay, thank you. Okay, so this year theme is focused on production logging. This is our fourth webinar. Will be with Baker Hughes company presented by Mr. Hussein Al-Shabebi. We plan to do a 10th webinar this year. Next webinar will be a combined webinar between open field and all service regarding flow array tool. It's multi-array tool by open field, and it's been utilized by all serve in Dubai and Iraq, other places. Next one will be Schlumberger, Kappa regarding software and so on, and we'll keep you updated. I'd like to thank all our sponsors for this year. Schlumberger, Baker, TGT, GeoActive, Allseer, Openfield, Kappa, and ISP. As usual, as last year, we'll provide a special certificate for the personnel that will attend 6 webinars and more. And if you are like working in Iraq or like to join our chapter, okay, it will be welcome to change your chapter affiliation to Iraq chapter. Question and answer will be left at the end of lectures. If somebody, or you can write it on the chat box and try to answer it at the end of lecture. Okay, that's all from my side. And if Dr. Mohammed like to have a word.
Yes, Mr. Mazen. Dear attendances and dear Mr. Hussein Al-Shabebi, this is Muhammad Jawad Zain Al-Abidin, Vice President of Technology at SPWLA Iraq Chapter and Senior Faculty Member at Petroleum Engineering Department, College of Engineering, University of Kirkuk. SPWLA Iraq Chapter would like to present to you for the fourth webinar in 2024 in regard production array imager production logging system tool. We hope you have a great time during the webinar. Thank you for everybody.
Thank you, Dr. Mohammed. And the mic for you, Mr. Hussein. You can introduce yourself and start webinar.
Thank you, Mazen. Thank you, Dr. Mohammed, for the introduction and for the opportunity to present to SPWLA Iraq chapter. My name is Hussein Al-Shabebi. I have a bachelor degree in petroleum engineering. I joined the oil industry in 2006. I spent 9 years with Schlumberger and 9 years with Baker Hughes, currently with Baker, mainly working on cased hole activities from well integrated to production logging and pulse neutron measurements. I'm sharing my screen. Please let me know if you can see it.
Yes,
we
crystal
can.
clear.
Yeah. Okay. Hi everyone. Today I'll be presenting to you the Baker Hughes portfolio of array production logging. So basically in Baker we are having 3 tools. I'll start with the old generation, and it is still current available, which is known as MAPS, which is the multi-array production suites. Then the new generation that we have, and it is commercial, it is a production array imager, PAI. And the third one, and still it is under trial field test, it is named as gas oil water array tool, GOWAT. We'll cover all these tools in terms of the design, advantages, and also some examples of them. So basically, the agenda will be the production logging application, followed by the introduction, a quick introduction of the multi-phase flow regimes, and how the flow regimes affecting the tool selection. Then our flow loop in Houston, how we are utilizing it for all these tools characterizations. Then we'll cover the three tools that we have, MAPS, PAI, and GOAT, with some examples and ending up with the summary. So starting with the production logging objective, so the main objective for any production logging is to know each well how much it is producing. But this information can be obtained from the GOSP or from the surface measurements. So the main advantage of the production logging is to investigate the production downhole. So for example, over here, as you can see, we are having a cemented liner section with 6 perforations highlighted in red in the well sketch track and in the zone track. So the main objective for any array production or for any production logging, either conventional or array, is to know each perforation, what is the phase that is producing and how much of each phase. As you can see in this example, so the gas production is coming from the last 3 perforation, and the oil is coming from the top 3 perforation, and the water is coming almost from the top 4 perforation. So this will help actually to diagnostic what is the interval that is producing the unwanted fluid like water or gas for early breakthrough, for example. Or also it can diagnostic if you are having any well integrity issue, like for example, if you are having a leak that leak is producing inside the wellbore, then the production logging tool can detect it. If it is insignificant amount, that it can help to rotate the spinners and overcome the thresholds of the spinners. Also, if the leak is behind the pipe, for example, you have a channel in the cement, then you have to add another tools, like for example, the pulse neutral tool with oxygen activation if this flow is water. But even if it is gas or oil, also you can run the noise log to investigate what is behind the pipe. So all this will help you to diagnostic the well and understand the performance of the well, understand the zones that is underperformed or not producing, and it will help you to design your remedial action to put back the well in the design, the desired performance. So the selection of the production logging tool, it depends heavily on the flow regime itself. So as you can see in this image over here, this is the vertical well. The flow regime usually in the vertical wells is homogeneous, either it is single phase or bubbles. So the distribution of the holdup and the velocity is almost homogeneous. So a single spinner or a single props for holdup measurements, it can be applied to achieve the production profile objective. As the well start to go in deviated or very horizontal, then this flows, it will start to segregate, and it will the flow regime will be much complex for the single measurements. As you can see over here, we are having a single spinner that is touching the gas at the top and the water at the bottom. And usually when it is horizontal, these velocities are not equal. It depends on the deviation. If it is slightly higher than 90 or less than 90, then this measurements, it will not be achieving the objective of getting the profile, the production profile. And from here, it comes the need of getting the array measurements. We are in Baker Hughes. Usually we are performing or investigating all our tools in our flow loop in Houston to check the sensors, window operation, the limitation of the tools, where to apply it, etc. So for example, over here, we can see in this image, we are having 2 pipes, and these 2 pipes are 6-inch ID. And these pipes are transparent, so we can visualize the flow regime. And the horizontal one over here, the blue pipe, it is 90 feet long. It is almost horizontal with plus minus 5 degrees. And this red one is vertical. It is 50 feet long. It goes from 0 to 90 degrees. The capacity of each pipe, they are similar, so it can take up to 22,000 of water plus 22,000 barrels of oil plus 200 standard cubic feet of air. Similar for the other one as well. And usually we are putting our tool in this flow loops to characterize the sensors. And for this one, we have to have independent measurements to compare the results. So for the hold-up measurements, we are having two sensors. The first one is the quick close valve, as you can see in this image, and we are having two of them. So basically, this quick close valve, it will trap instantaneously a sample of the flow in the pipe, then will allow it to drain. And from after draining, we can identify how much holdup of each phase at that cross section. The other measurements that we have for holdup as well is the micromesh that I'll cover in the next slide. And in terms of rates comparison, we are having a high precision micro motion flow meters. In addition, also if the flow regime is bubble, especially in vertical, we can use the micromesh as well. So this is the micromesh that we are utilizing for hold-up characterization as well and measurements. As you can see, we are having two of them with a known distance. Each one, it has 32 by 32 knots of capacitance. And this is a real example from the flow loop. As you can see over here, we are having 8,300 barrels of water with 14,000 of gas, standard cubic feet per day. And it is in horizontal section. And you can see the flow regime that is wavy, stratified, and it is reflected very nicely also in the capacitance and the micromesh. In this example, we are using also, as I mentioned, the micromesh to calculate the velocity. So we are having two micromesh with a known distance between them. And usually we are utilizing this if it is a bubbly flow because we can see the bubbles that is traveling from a first micromesh to the second one, and we can generate the velocity distribution. This is the same example that we have seen before, 8,300 barrels of water with 14,000 standard cubic feet of gas, but this is vertical to generate the bubbles because usually this one is not, we cannot utilize it in the horizontal. This slide has been covered before in this chapter, just as a quick refreshment. So this is the flow regimes in different angles. The first one over here, you can see it is a vertical pipe. The flow regime is homogeneous. As you can see, the oil and water traveling very homogeneous and steady. As the deviation, as the well is getting deviated, these things will be changed. As you can see now over here in 89 degree, the oil holdup is getting small and the water holdup is getting large, and it's also this affected the spinner's velocity. As you can see in oil, it is traveling faster, and in water, because it is occupying larger area, it is traveling slower. And as we change the deviation only to 2 degree to 91 degree, you can see the different things are changing. So the oil now is occupied more area compared to the water will occupy small area. But also this will be reflected back to the spinners. Now you can see the spinners in the water will be rotating faster compared to the spinners in the oil. Because the rates in both all of these examples, they are similar. It is 1,000 barrels of water and 1,000 barrels of oil. Just to show how the deviation, it is changing the flow regime itself. Here, another two examples, just to show how things can get complicated. So what we are having over here is 600 barrels of water with 600 barrels of oil and 3,000 standard cubic feet of gas, of air. As the deviation is getting only 89 degree, slightly 1 degree from the horizontal, you can see how the air is slugging. And also you can see there is a mix or bubbles between the gas and oil layers over here. And just putting it back to 91 degree, you can see things is getting more stratified now. The oil, the air at the top, you can see a little bit mix between air and oil, and the water is stratified at the bottom. So just 2 degrees change in the deviation, it can change the flow regime very drastically. So this slide is just to highlight some of the challenges that we are facing with the array production logging. So the first challenge that we are having is the complex flow regime, and this is usually happening when we are having very highly deviated. So in this example, the deviation that we are having is 65 degree with 44,000 barrels of liquid with 30% water cut and 200,000 standard cubic feet per day. And you can see the recirculation is affecting our tool response as the air is slugging, is going up, trying to push the liquid to the top. And because of the gravity, it is falling back. And usually this is very difficult to characterize. Other challenges that we have also is access of multilateral wells and also the debris and asphaltene that it can block the sensors, either spinners or props, the hold-up measurements. Emulsion also, it can give you wrong indication of the phase that you are calculating. Limitation of the convenience method, especially for the very long access wells. Instability of flow, because to get a representative flow profile that you need the well to be stable. Open hole and washout, especially if this is beyond the tool maximum opening. And low flow rates, especially if it is below the spinner's thresholds. So the first tool that I'll introduce to you is our MAPS tool that is also run by many service companies. So this tool actually it has 3 modules, as you can see, and usually these modules between them we are putting a centralizer to centralize the tools. So the first one we have is the SAT. So we are having 6 spinners in this module with 6 arms in bowspring, and this is for velocity calculation of the fluid. Then the next one we are having is the capacitance array tool, which is known as CAT. We are having 12 sensors that it can differentiate between oil, water, and gas. And the third tool is a RAT, resistance array tool, that it can differentiate between hydrocarbon and water. And we are having 12 sensors as well. So basically, as you can see, this sensor are distributing at the circumference of the well. And usually the software, when it is applying this, it will try to segment the cross-section horizontally. And from each segment, it will try to calculate the local holdup and the local velocity to calculate the local phase rate. And then it will sum all this phase rates to final getting the final QO, QW, and QZ at that depth. And this is happening. This calculation is happening at every depth. So the first tool that we are having in the maps is the resistance array tool that is very depending on so to differentiate between water and hydrocarbon, basically it is based on the conductivity of the fluid. So as the salinity of the water is increasing, the conductivity will be higher. And this example is done in the flow loop. As you can see, we are doing the measurements for different salinities, starting from 107,746 ppm up to 203 ppm. The green one at the bottom is the very high saline water, and this blue at the top is the almost near to the fresh water. So as you can see that the response of the sensor, it is the dynamic range between the oil or the hydrocarbon usually reading is around 0.9 to 0.9 to 1. So you can see the dynamic range between the hydrocarbon measurements and the very saline water is very high. As the salinity decrease, the dynamic range between the hydrocarbon and the water is getting less. But still up to 203 is very fresh water. Still the tool can differentiate between the water and the hydrocarbon. As the maximum reading over here for water, we can see it is 0.7. The next sensor that we have is the capacitance, and this test was done again in the flow loop. What we are changing over here is the water cut and also the liquid rate. So we started with 9,200 barrels of liquid up to 22,300 barrels of liquid. As you can see in this plot, as the water cut is increasing, we are losing the oil sensitivity when the water cut is reaching around 40%. And this is the limitation of the tool. So basically, if the water cut is higher than 40%, usually this tool is not responding very well. But when I'm saying 40% of water cut, this is in mix flow regime. But usually when it is segregated horizontal, since the oil is separated from the water, even if the water cut is producing very high water cut, even if it is close to 99%, if it is segregated, still the tool is working. So this limitation only in mix flow regime. The next tool that the new generation that we have is named as PAI, Production Array Imager. So what we are trying to do in this tool that we are combining all the three modules in one module now. So you can see now all these 6 arms. Every arm, it has 3 sensors. Starting from the spinners, which is similar to what we have in maps. It is basically for velocity measurements. Resistance, it is same what we are having in maps to differentiate between hydrocarbon and water. And we just replaced the capacitance with the optical sensors. And the main reason that we had to have independent measurements for the gas holdup, which can differentiate between gas and liquid. Because the capacitance, it has limitation that the dynamic range between the gas and oil is very small. And usually it's very difficult to calculate and utilize it for the 3-phase holdups. Then, as I mentioned, all the sensors now are co-located. Also, we are changing the arms. It is more robust compared to the bowstring in the maps. And you can see also the tool length now is reduced almost by 50% from the maps. So maps, it has 12.3 feet length with centralizers. This is for PAI. For maps, it is 23.4 feet with centralizer. The operation limitation for this tool, it can goes up to 350 degree Fahrenheit and 15,000 psi pressure. The tool OD is a little bit bigger compared to maps. It is 2.125, and this is to accommodate all the sensors in one place. And also the maximum operating diameter is 9-inch compared to 7-inch in maps. Each sensor as well, it has its own deviation sensor and relative bearing. So for the optical sensor, basically the old generation of PAI or the first generation of PAI that we have, we were using a conical optical sensors. And usually the principle is very simple. It depends on the refractive index. So if the fluid is reflected back, it is in gas. So it means that gas is surrounding the tip. But if it is refracted, it means it is liquid surrounding the tip. So over here in the next few slides, just a quick comparison between maps and PAI. So the first thing, as you can see, the length, including the centralizer for PAI, it is 12.33 feet, and the weight of the tool is 68 pounds. While in maps, including the centralizers, is 23.43 feet with 103.3 pounds. So you can see almost 50% reduction in the tool length, which will help us to run the tool in high dog leg compared to maps. This is also the view of the sensors, how close to each other. So you can see the optical sensor and the resistance sensors, they are opposite to each other and they are at the same depth in the horizontal section. And you can see the difference between them, it is only 20 millimeter. Over here, between the spinners, the mid of the spinners and the tip of the sensors of optical and resistance is around 200 millimeter. And this is will help us, especially in the very complex flow regime. That's, for example, the slugs. Now that all the sensor can see it at the same time. Before in the maps, they are at different depth. So you can see one slug at cat and still you are not seeing it at trot, for example. As I mentioned as well, these arms are more robust and they are independent, so they can take the shape of the hole if it is circular or elliptical. Also, we can restrict this arm independently before running in hole. It depends on the objective. And as I mentioned, these arms are independent. You can see over here that if this is fully open, we can restrict the opposite one. While in maps, they are connected. So if you close the opposite, if you close this one, the opposite one will close as well. So this will help us to tolerate the decentralization as well. Uh, this slide to show you how important is that allowing the tool to touch the top side of the wellbore because this decentralization can enhance some of the errors in the measurements. So in this example, you can see this one is around 89 degree with 1,000 barrels of oil and 1,000 barrels of water. You can see the oil is occupying very small layer at the top side of the wellbore. If we are putting the deviation at 91 degree, you can see now the water is occupying a small portion at the bottom side of the wellbore. So if the tool is decentered only by 0.5 inch, then it means that our sensor is at this location. So basically, if your oil is above you, you will not see it, and you will see almost 100% of water. So if it is only 4% error, it can introduce to your measurements. And this is also important. For example, if we are having, let's assume we are having a sensor at this depth, which is 19.6%, then the next sensor at this depth is blinded, for example, is not working. Then and the next one is at this depth at the center of the wellbore. So you can see now the error. Usually the software, it will interpolate between this sensor and this sensor, then since this one at the between is blinded. And you can see how much error between them is almost 30% error between them. So when you are interpolating, you are reducing it to 15%, but still showing how important to have good measurements or more sensors in the wellbore to reduce these kinds of errors. This is again to show you the effect of the eccentricity of the tool. So at the top images over here is the tool is very well centered, and the bottom images the tools are 0.5 inch decentered. So the left images over here is comparing the SAT sensors. As you can see, when the tool is decentered, the top arm, the opposite arm of this one as well, it is collapsed as well. And you can see now it is not touching the wellbore at the top side. Similar thing for RAT, as you can see over here, when the tool is very well centered, you can see both sides are contacting the wellbore or the inside wall of the pipe. But when the tool is decentered, you can see the opposite arms as well is collapsed, and we are losing the sensitivity of the measurements at this area. PAI, as I mentioned, it is independent. So even if this arm is collapsed, the opposite arm will open more, and it will still keep the contact with the pipe ID, unless if it is more than the maximum opening of the tool. So for each arm, the maximum opening is around 4.5 inch. So the new generation of Pi, we are trying also to improve it. So basically what we are trying is to evaluate the differences between the conical optical probes and the biconical. So on the new generation of Pi now, we are utilizing the biconical sensors because of the advantage that I will mention in this slide. So basically intensive the study was performed in different kinds of angles and also different type of coating, because what we observed in the conical, it is very easy to be coated and getting wrong measurements. Different type of coating material, either permanent or semi-permanent, was utilized, but still it is not a permanent solution. It can mitigate the coating effect, but still it will happen. Also, the angle of the biconical of the tip itself, it is affecting the measurements of the refractive index. So we were using optical simulation software, and also we were using a Monte Carlo tracer coding to evaluate the best combination of the angle and also the wavelength. And we were also trying to introduce the fluorescence measurements to the refractive index as well, because it will help us to differentiate between the water and oil. Because oil, it will have the fluorescence, and water and gas, usually it doesn't, the fluorescence when the sensor are in gas and water. What we observed as well, this fluorescence is affected by the oil gravity. So as the gravity of the oil is getting very heavy, the fluorescence will be very small. Uh, and the wavelength, it also depends on the asphaltene absorption contents of the asphaltene in the liquid, in the gas as well. So the best option that we found is always the wave. We are using two kind of waveforms, infrared, and we are using 870 nanometer. And also we are for the fluorescence, we are using the ultraviolet light. So just to highlight over here, the refractive index from the biconical, we are utilizing it in new generation of the PAI, but the fluorescence is still, we are not utilizing it in PAI, we are utilizing it in GoWatt tool. So in GoWatt, we are using the biconical that it has two measurements, refractive index and the fluorescence. In this example over here, we are having a cup that it has air at the top, then oil, then water. So as we are dipping the probe of the optical, you can see the reflection, the reflected is in red color over here, is very high when it is in gas, then it is very low when it is in oil, and it is medium when it is in water. And the fluorescent response, as you can see, for gas and water, it is very low. In oil, we are having high fluorescence. So if we combine these two measurements, the refractive index and the fluorescence, actually from the optical sensor itself, we can get the three-phase holdups. This is another example from the flow loop comparing the conical and biconical. So in this left side of the image, in this track and this track, so this is the histogram of the biconical, and this is the wavelength, the waveforms, and the right tracks is for conical probes. So we started with the static water inside the pipe. As you can see, the refractive index is reading low in both conical and biconical. Then we introduce oil to the pipe. Then you can see now in the biconical, we can see a change between the water and the oil. But in the conical one, almost it is the same. There is no change. Then we introduce gas, and you can see now we are having three phases. The very low value is for oil, the medium one is water, and we are having the gas peak at very high histogram. But in here, in the conical, it is only differentiating between liquid and gas. And also another observation that we have, that always if you see the biconical, the baseline for the gas is very stable. But if you compare it to the conical one, it is unstable. So this actually will help us to get the baseline for accurate hold-up measurements. While over here, if you set your baseline, you can miss some of the hold-ups measurements. This sensor, also we are adding it to GoWatt. So basically GoWatt, it is similar to PAI. It has three sensors, SAT, the spinners, the optical sensors that it has two measurements, refractive index and fluorescence. And we are replacing the resistance with the piezo Helm resonator. So basically, what we are trying to achieve from the piezo Helm resonator is to overcome the resistance limitation. As you can know, the resistance is easy to get blinded, and also when the velocity is very high because of the small bubbles, you can miss, especially in the mixed flow, we can miss some of these bubbles. So we are trying to get from this measurements the density and the viscosity to overcome these challenges, and also it will help us in the emulsion. One of the limitation of the resistance, that if it is you are running it in emulsion, you will read the continuous phase only. But from here, with the help of the viscosity, we can determine if you are having emulsion in this well or not. This tool, it has to be calibrated as surface before running in hole. So basically, this is the tool that we are running is very tiny. So we are running six of them in one on each arm. So basically what we are doing is measuring the resonance acoustic of the flow that is running between these two tines, and utilizing the fast Fourier transformation and phase shift. We are converting that to density measurements and viscosity measurements. So this is an example from the flow loop. As you can see that when we are reading in the air, this is the frequency response, and we are converting that to density after calibrating it at surface. The other application of the piezo hem resonator, as I mentioned, is the emulsion. So what we are trying to do over here, still this work is in progress. As I told you, the GoWatt tool is still under field trials. So what we are trying to do over here is to convert the emulsion content to hold up measurements. So what we observed that the full width half maxima and viscosity, the relationship is exponential, but up to a certain water cut, up to 30% water cut. Above 30% water cut, you can see that the shape is reversed and actually it is decreasing. So what we observed that when the water cut is from 0 to 20%, the oil phase is the continuous phase. And from 30%, it will be changing. The water will be the continuous phase and oil will be the bubbles inside. This is the example from the flow loop of the GoWatt. So in this track, we are having a refractive index response, and this is the mean average. In this track, we are having the fluorescence histogram and the average. And in this one is the piezo hem resonator density. And this is the spinner's response. So we started with flowing oil and gas at 1,000 barrels of oil and 200,000 of standard cubic feet of gas. As you can see, we are having oil response in the histogram, and also we are having the histogram peak at the gas response as well, telling us that we are having two phases in the system. The fluorescence is responding as well because we are having oil in the system, and the density is reading a little bit higher from the gas value. Then we're introducing the water and we stopped the oil. You can see now the histogram for the water, the oil is decreased to the water value, and still the gas is almost at the same peak. The fluorescence is decreasing, but it is not going to zero because actually the separator is this flow loop. When we are trying to flow the fluid inside, there is no enough time for the separator to separate the liquids. So there is still some traces of oil is flowing with the water. Also, you can see the density is increasing because now we are having water in the system. At this depth over here, at this time, then we stop the gas, and now you can see now we are having only water in the system. We have one peak only in the histogram refractive index. The fluorescence also goes almost to zero, and the density is increasing almost to the water density value. This is for the array tools. Other application also that we have in Baker is the pulse neutron tool for oxygen activation application. And usually we are running this tool in very complex environments, like if the spinners are sticky as not rotating and you are trying to get the water entries, or there is a leak of water behind the pipes. So basically the principle is very simple, that we are having the source that is firing neutron. Then this neutron, it will collide and interact with the surrounding of the tool. And when we are running in oxygen activation mode, it will activate the oxygen, and this oxygen activated, it will generate a gamma ray. And the half-life of this gamma ray is around 7.13 seconds. If the flow direction it is passing the detector, then we'll be able to detect it. So as you can see over here, the source on the left side and the detectors are on the right side. So if the flow is going on the right side, this detector will be able to detect the gamma ray from the oxygen. And knowing the distance and the time between the source and this detector, so we can convert that to velocity. But if you are the flow in the other way of direction, then you need to invert the tool to put the detectors on this side. We have two options for the oxygen activation. We are having a stationary measurements, which we name as a flow shots, and also we can do a pass measurements, which we name it as a hydrolog, which it has the same principle. Both of them, it depends on the oxygen activation. And the final one that we have also for the holdup, if you have difficulties with the array sensors holdups to get the holdup inside the wellbore, we can utilize the pulse neutron tool to get the holdup from the pulse neutron holdup imager, PNHI. So we are running it similar to the CO mode, carbon oxygen ratio. So basically, if this ratio is reading very high, it means almost we are having oil in the wellbore. If it is reading low, it means we are having water. Also, we combine it with the inelastic ratio measurements of the short and long sensors. We name it as NF, which is very sensitive to gas. So if it is reading high, it means it is liquid. If it is reading low, it means it is reading gas. Uh, but as I mentioned, when you are firing the neutron, it will interact with all the surroundings, casing, cement, formation, and also the wellbore. So we need to try to minimize the effect of the casing, cement, and beyond. So what we are doing, we are trying to build a model, Monte Carlo model, based on the scenario that you have, to eliminate or to minimize the effect of the formation and the wellbore, the casing and cement. And we are utilizing a triangle method to convert these measurements to the holdup measurements. Now I'll start with the examples. The first example that we will have is for maps. This is to highlight the completion damage. In this well, we are having screens isolated by packers in compartments. And the objective is to get the flow profile, identify the water entry. This is the image of the holdup. As you can see, the middle is the top side of the wellbore, and the bottom side is the edge of this image. This is the spinner's distribution for the down and up pass. This is the holdup measurements from these sensors, converting the array or the image to one holdup measurements. This is the rate calculation Q, W, and QO. And this is the mixture water velocity. And this is the constructed profile. So what we can see over here that we looked up around 38 feet above the end of the screen. And from that, what we can see that we are having almost 40% production is coming at the maximum depth that we reach. So it is either two options, either that the last 38 feet that we couldn't log is damaged, that's why it is producing a high amount of liquid, or the plug at the bottom of the completion is leaking and still it is producing that amount of water and a small amount of oil. This is one of the benefits of running array production logging tool is to evaluate the integrity of your completions. The second example is to show you a emulsion case and the advantage of running the capacitance compared to the resistance. So over here, we are having a down and up pass for the capacitance, similar for the resistance. And you can see the resistance is because it is oil continuous phase, it is giving you hydrocarbon almost. But if you look to the capacitance, it is showing you that you are having a mixed flow. In emulsion, the limitation, it has to be less than 40% of water cut. Otherwise, it will be saturated, as explained before. So over here, the water cut was around 39%. Because also you can see it is segregated at the bottom. We are having high content of water at the edges. And as we going at the top, the water contents inside the emulsion is getting less. So this is completed with ICD, again, isolated by packers in compartments. And the main objective is to identify the water entry, and from the response of the capacitance, the water entry is producing from the top zones, as you can see in the constructed profile over here. So we run it in two rates, low rate and high rate. And what we observe in the high rate also that there is increase, if you compare to the low rate, this second compartment was not producing any water, but the high rate, it was producing very small amount of water. So this could give us indication as well that this packer also could be partially leaking. As more drawdown, we are getting the water reaching up to the next compartment as well. So what the client was did, they put this in NetTool, the results from the PLT, trying to simulate if they close the top compartments, what will be the production profile. And after testing from the ghost results, what they observed that the water cut was reduced by almost 62%, and the oil production was increased almost by 51%. And this is published, this paper is published in IPTC 2029-7. The next example again is for emulsion, just to highlight the importance of the advantage of the capacitance over the resistance measurements. I will highlight only the important tracks over here. So over here we are having the capacitance response of one sensors only in flowing condition, and in this track it is in shutting condition. So usually if you see the shutting, that usually the emulsion is separated and we are having zones, depends on the trajectory. As you can see, the lower zones it has water accumulated, and the higher zones it have oil accumulated. So we took this as our baseline for normalization. As you can see now, when we are flowing, the capacitance response is not going to 1 as over here. It is in between almost. And you can see the steps over here. It's showing you that the water increase in this screen over here, telling us that the water entry or the major water entry is happening actually between this X and Y zone. And another indication of the emulsion always that you will see that the spinous distribution always it will overlay because it is almost homogeneous flow regime. So you don't see a difference in velocity between across the cross section itself. But if you look over here to the resistance image, you can see the resistance image, it is blinded, or it will give you, it is actually not blinded because actually the water is inside the oil film. So it will just measure the oil bubbles itself or the continuous phase. This is the last examples for maps that highlighting emulsion presence, they again in combination with a leak in the completion. So basically we are having ICD completion compartments isolated with open hole packers. As you can see over here, we are having in the last compartments only 2 ICDs, but the response in the capacitance in this track, you can see actually it is happening between them in the blank pipe. There is no ICD in this depth, at the X depth. If you see the resistance response, it's showing that we are having a water sump below this depth. There is no production. Then we are having almost 100% hydrocarbon. But actually this well was producing a 25% water cut. And capacitance was able to detect that one because still it is within the operation limits for the capacitance, which is less than 40%. We can see that this there is a leak at this depth. And the profile was constructed based on that. And this is the temperature response. I'll show it, I'll talk about it in the next slide in this one. So over here, what we can see, the spinners overlay. So there is no velocity distribution. It is almost the same because of the emulsion presence. And the temperature is reflected across these entries, as you can see. So for example, in this middle one, we are having 3 ICDs. There is no temperature reflection, and the spinners is almost reading flat with small entries, maybe below the spinner's resolution. Over here, we are having 2 measurements, and this one as well, we are having a reflection. But the main question was this ICD, there is no reflection in temperature. But if you look to the spinners overlay, there is very clear indication that we are having entry at this ICD. It is not reflected in temperature. So that's why always temperature utilizing is more qualitative than quantitative measurements. The last example that I'll cover is both PAI and GoWatt in one run. So we run it together in the whole. The first sensor that I'll talk about is the piezo Helm resonator to calculate the density in the vertical section. So we are having 6 measurements in the vertical section. As you can see, they are almost consistent, and we run 6 passes. And this is the derivative from the pressure density measurements, and you can see they are almost reading the same value. It is reading a little bit higher from the gas value. It is a gas dominated well. It means that we are having a liquid as well flowing with the gas. The next sensors comparison that we have is conical from the PAI tool, which is in the left side image over here, and the biconical sensors, which is in the right side images over here. So I selected only 3 sensors to present. We are having 6 versus 6. So as you can see over here, they are almost reading the same, very high gas content. It is almost the comparison or the average readings from the conical, it was reading around 98%, and from the biconical, it was reading around 96%, which is very close. But the main advantage, as you can see, the baseline for the gas is differ in the conical. It is changing, while it was very consistent in the biconical sensor. And this is one of the main advantage. And this is could be affecting and introducing this difference in error, 1.8% between the conical and the biconical. The next sensor that we have in the tools is fluorescence, and we are comparing it with the resistance from the PAI. So fluorescence, we are getting it from the GoWatt tool, and the resistance is we are getting it from the PAI tool. So this tracks over here is the resistance 6 track, and you can see they are reading almost 0, so they are not detecting any water. And over here, the fluorescence is to get the oil. So basically, you can see we are reading a little bit high from the 0, which is calculating to be around 32%, 3.2% of oil that we have from the fluorescence, while 0% from the resistance. And this is the advantage of the fluorescence, combining fluorescence with the optical sensor refractive index, that this around 0.8% difference now between this and the previous measurements. If you recall over here that we are calculating around 96% of gas, so we are having 4% remaining, and now we are getting 3.2% of oil, so we are remaining with 0.8%. That is water basically, because the well from the surface measurements, it was producing water as well. The resistance were not be able to detect it because of the high velocity, and this is one of the limitation of the resistance tools, that when the bubble size is getting very small because of the high velocity, it will be missed. All these measurements that I was showing in the vertical section. So this slide is in the horizontal section and combining all the measurements together. So I'll start from the left side. We are having, I selected over here 4 sensors of the density. This track and this track is in the top side, and this one is in the middle, and this track is in the bottom of the cross section. This is the tool orientation. This is the resistance image, and this is the fluorescence image, and this is the biconical, and this is the conical. So starting from the bottom of the wellbore, you can see that we are having sump of water. So all the densities is reading almost 1.1. The resistance is showing very clear that we are having a conductive material. Over here, the fluorescence is showing that absence of fluorescence. It means either it is gas or water. Gas and or water. And the optical sensors, both biconical and conical, showing that we are having a liquid. So combining all these measurements, we can interpret this as a water that we are having at the bottom side. As we go higher, we can see now the densities are dropping. At the top side, you can see it is reading almost gas, and it is reflective in the biconical and conical image over here. Also in the fluorescence, you can see the top side, there is no fluorescence, means we are having gas. And from the resistance, because it cannot differentiate gas from oil, but at least it's showing us it is a hydrocarbon. As you can see, also this water sumps over here is reflected as well in the fluorescence very nicely. And this water sump as well at the bottom side, you can see it in the fluorescence over here as well. So combining all these four measurements together, we can get more confident hold up measurements to utilize it for the rate calculations. The other application that I mentioned is the pulse neutron. So this example I selected for from the pulse neutron that we couldn't run the spinners because of the sticky materials. It is open hole with 8.5 inch open size. So this is already converted to the rates. So basically we are utilizing the PNHI as well, the hold up measurements and the area from the caliper. We convert that to rate. The green curve over here is the continuous measurements, the hydrolog, and the dots over here is the flow shots. And you can see they are consistent, and we are getting a confident profile at both high rate and low rate. The only difference that we see is this dots over here for the flow shots is a little bit high in the low rate. And this is mainly because if you see the deviation over here that we are having this high deviation, which is favorable for the recirculation. That's why you can see that the upward water is occupying small and most of the water is falling back again. That's why it is giving high velocity. And this is a PNHI example. We are utilizing two measurements from the pulse neutron, the CO, and also the inelastic ratio between the near and far detector. If the carbon oxygen ratio is reading high, it means we are in hydrocarbon. If it is reading low, we are in water. Then to differentiate this hydrocarbon between oil and gas, we are looking to the near far inelastic measurements. If it is reading low, it is gas. And if it is reading high, it is oil. In summary, quickly to summarize this one. So basically the advantage of the PAI over the maps is one of the tool length. So we are shortening the tool by 50%. Also the arms is more robust compared to what we have in maps, that it can tolerate the decentralization. The sensors now are collocated to overcome the complex flow regime. Also, the coverage of the cross section, we are increasing it to 9-inch compared to 7-inch in maps. And all the sensors were heavily characterized in the flow loop. And also still, as I mentioned, we are improving the sensors by upgrading, for example, the PAI from conical optical sensors to biconical, and also trying to upgrade from PAI to GOWAT to include the fluorescence measurements with the refractive index, and also to utilize the piezo Helm resonator to overcome the resistance measurements. By this, I'm ending my slides, and the floors are open if you have any questions.
Thank you, Mr. Hussein. Hello?
Yes.
Yes, you can hear me. I believe there's
Yes, yes.
Amr Yusuf. Can you close your camera, please? Amr? Hello? Does he take a big chunk of the recording? Okay. Thank you, Mr. Hussein, for your informative webinar. Okay, it was really useful for us, and hope it was useful for the attendees as well. And let's see if somebody. Okay, I cannot see any question on the chat box. If anybody have any question, okay, if not, I have two questions as well. Mr. Ahmed Abu Zaid. Yeah, you can jump in, Ahmed. You can open the mic.
Yeah, thank you, Mazen. Thank you, Hussein, for the great presentation. I'm just like wondering what the benefits of the co-locator sensor to improve the data. If you can elaborate more for this, maybe you covered, but I didn't get what the value of having these features.
Yes, I can go back to this slide over here. Let me run it. Yeah, so basically, if you look to this image, when the flow regime is getting complex, that you can see the slug is passing at very small area. So if you have the sensors co-located, you can see this slug at the same time. But if you have one sensor at this depth, another sensor at this depth, then you will see them at different time. So this is the main advantage of having the sensors co-located. Does this answer your
Thank you,
question,
Hussein.
Ahmed?
Yeah, thank you, Hussein. Clear now.
No, thanks. I cannot hear you, Mazen, if you are talking.
Hello, you can hear me right now?
Yes, yes.
I believe my voice was muted. I was saying it was a really interesting webinar, and it's on advanced level. Okay, I believe on the region there is maybe very few people dealing with the multi-array tool, and it is really nice to have this webinar. Myself, I dealt with a few multi-array tool, and I can say this PI design is really one of the best, okay, because having 6 arm, what is the length of tool? I believe it's not that long, short.
No, it is 12.3 feet, yeah,
Yeah, 12.3 feet. So it's about like a
including
1
the
meter.
centralizers. Yeah.
Yeah, 1 meter. So this is and have 6 arms, so it will have a full coverage. Okay, as far as I
Yes.
understand, have 3 sensor per arm. 3 sensors.
Yeah, in every arm you have one spinal measurements and one optical and one resistance.
Yes, one.
And
So
also
what
these
is
tools are combined, so you can run two tools combined. And also it is combinable with maps. So if you are having, for example, emulsion, well, that you don't know if it is emulsion, you can run pi combined with cat as well.
Yeah, this is great. Yeah, like I believe this tool will have a really big future. Okay, to have such short tool have all this full coverage. Okay, you can get all the answers you need in highly deviated well. Okay, and horizontal. And by the way, like in Iraq, we have a lot of not horizontal, like a highly deviated well, and we suffer a lot of these recirculations, low flow rate zone, or some S14 zone. Okay, this is the thing. So just I have a few questions, okay, if you don't mind. So for
Yeah, please
this,
go ahead.
Sondex was belong for GE. It is belong for Baker right now after Sondex.
Yes, now it is with Baker.
So it is under Baker.
Yeah.
Okay, and this JA tool, JAT, I saw some runs even in Iraq, like they combine JAT. It is only the optical tool they added to maps, as per my understanding.
Yes, now after introducing Pi is inclusive for Baker use only. As you know, Maps is run by many service providers
Yes.
because Pi it has optical sensor. Then also they generated a GAT, which is a GAT, to just complete the modules for the Maps itself. So now for the new generation of maps, you will have SAT plus CAT plus RAT and GAT as well.
This is great. And this is, I believe, MIMS is like miniatures of sensor. The sensor in the GAT is similar to the sensor in PyTool, or it is different?
Yes, it is similar.
Okay. Okay. For this Pi, you said there is like it is on field trial, or it is like final, or only the
GoWatt, not
viscosity.
Pi. The GoWatt tool.
The
So basically, the difference between Pi and GoWatt, the biconical optical sensors, for Pi, it has only the refractive index, but for the GoWatt, it will have the refractive index plus the fluorescence. And also the resistance in Pi, but in GoWatt, it is a piezo-Helm resonator, that it will give you two measurements, density and viscosity.
This will be really great because sometimes have commingle production. I want to see which formation is producing what. Okay,
Yeah.
this will be really useful. So which countries like it have been used this Pi like it? For sure in Saudi. Okay, but
Sorry?
like, PAI. In which country have been used? Like where it is used?
PAI we are utilizing it here in Saudi and in different locations as well. I believe UAE as well, they are having it. Oman. We are running it globally in different places.
Okay. Okay. Let's see
The
if we have
GoWatt
more
still it is only in Saudi under field trials, and still we are working on it.
Yeah, hopefully it will be finalized at some point. Really interesting too. Nothing from my side. Okay. And if nothing from audience, Dr. Mohammed, do you want to say last word before we conclude?
Thank you. Yes, thank you, Mr. Mazen. Mr. Hussein, thank you for your great webinar. We would like to continue with you really, with your very significant lectures in production logging. Thank you, our attendees. Yes, thank you again, our attendees, about accepting our invitation today in the fourth webinar for SPWLA Iraq chapter. Thank you.
Thanks all. And thank you, Mr. Hussein. I'd like to thank Ahmed Abu Zaid also for coordinating this webinar from Baker Hughes, and I'd like to thank Baker Hughes as well, and our attendees.
Thank you. Thank you.
Thank you, and see you
Have
next month.
a great
webinar.
day.
Have a great. Thank you all. Bye bye.
Have a nice time. Bye.
Bye bye, Dr.